Welcome to Unit 4 of COMP526. In this unit, we will talk about string matching. That's the fundamental problem of finding a certain piece of text in a certain larger piece of text in that generality. I put it with a subtitle, What's Behind Control F? Because the ubiquitous search functionality in all programs, and especially in browsers and text editors, is very helpful to boost productivity. And people are very used to doing Control F all the time and find strings all the time. And in essence, what's behind this are exactly these algorithms that I will show you. And one of them that we'll discuss in more detail is what many of these tools use to implement this. To get started, I want to introduce some notation and some formalization of what strings and text is in our context so that we're all on the same page about this. Then I'll discuss the easy methods, how to do string matching, and which is often good enough, but not always, depending on your applications. And then we'll discuss a couple of string matching methods. String matching with automata and Knuth-Morris-Pratt is something you might have seen, but maybe not with that angle of explaining it. I think you will like it if you have seen it explained differently. Boyer-Moore is interestingly often beating the optimal algorithm here, so we'll discuss that riddle a bit. And finally, we'll look at Raven Karp, how hashing can help with string matching. Let's start with the notation and introduction. So what is this about? It's about strings, which are essentially just a sequence of characters. And it's, in a sense, the universal type for all sorts of data that is often the least common denominator used, especially on the web. Of course, we have natural language texts, just English text or text in any other natural language. But we also have programming languages, and well, the text in programming languages are source code. We have websites, HTML at the end is all just text. We have XML documents. Related to that, usual websites should be valid XML documents, but let's not get into this discussion. An entirely different type of text are DNA sequences encoding your genetic information. We have bit strings. It's not usually seen as a text, but the same techniques and algorithms can be used. So ultimately also, any computer's memory is just a long string of bits. So whenever you want to find a pattern in this, this might be all applied as a string matching algorithm then. There's many different applications, and that also means the tasks, what you want to do with strings and the algorithms to solve these problems are very different. What we will look at is a very simple and fundamental problem, but one that already has quite interesting algorithmic solutions, and we'll build on these for more advanced applications. So Control F is what I mentioned. Grep, the Unix command, or fgrep if you want. We'll not get much into regular expressions, but the extension is often not too hard. So these are classic tools that find occurrences of some pattern text in a bigger text file. You can also generalize this to computer forensics, where you scan large amounts of data for certain signatures of malicious files. That's what virus scanners do, etc. And many other applications essentially build on string matching as a stepping stone. So here's my notation for strings. We have an alphabet, and that's conventionally called sigma. The capital sigma looks like the sum sign, but it's the letter sigma in the Greek alphabet. It's any finite set of characters, and a character can be really a lot. Usually we think of them as letters in some alphabet, maybe the Latin alphabet that we are used to use, but it could be any other natural language alphabet. It's often also generalized to whatever you can type on a keyboard, or, well, whatever you have in the Unicode standard, including all the emoji and whatever. And it could also be very much restricted to just 0, 1 or the nucleotides in a DNA sequence. That depends on the application. An important parameter will be the size of the alphabet. That sometimes plays an important role. I will write sigma to the n with the superscript m to be the n-wise Cartesian product. So these are just all the strings of length exactly n. And we also call these n-tuples in general if this sigma is any set, so that's just generalizing standard notation from mathematics. Sigma to the star is all the strings of any finite length. So the union of all these for any n greater or equal 0. And it includes the empty string, this guy, which is written as this little epsilon. That's the empty string, and we sometimes want to write it, even though it's actually just nothing, empty, right? And something that's also useful as a shorthand, the sigma plus is all the strings that have finite size but not 0. That's that. And now I'm in the way. If we are given a string s of length n, then we just write accesses to these characters as if it was an array of characters. So we write si, s of I, for the ith character. And again, I try to be consistent and make it 0 based for all of this class. So we start with the 0th character and we end with the n-minus first. Some other texts or books use s subscript I, but I tend to find this closer to code and it's just as readable. So we will just stick to that. If we have two strings, we just write st to mean the concatenation, putting the strings next to each other, one after the other, and sometimes spelled out by putting a multiplication sign in between. And finally, if we have a string of size n, we write this notation, which is similar to arrays, for a substring that's formed from just these characters from position I up to j, both inclusive. If I is 0, we call this a prefix of s. And if j is n-1, we call it a suffix of s. So this is just something at the very beginning or very end of the string. Again, nothing magic about this. And again, something I introduced for arrays already is this notation with a round parenthesis, because we will often want to write positions I up to j, but excluding the endpoint. And so that will be with the round parenthesis. I hope this set of notations is somewhat close to what you've seen in other classes and won't be too confusing. But, well, just bookmark this slide in case you ever get lost or ever don't remember what something means. Here's a little question to test your understanding or check if you paid attention on this rather boring slide, maybe. Is it true or false that the sigma star is essentially sigma plus and the empty string for any alphabet? Okay, I'll give you a little bit of time. I went over this quite quickly, but it's a very simple question. It's essentially just making sure you're still awake. "15 people, that's half of the class. We have some more. You can be honest and tick no clue if you fell asleep during the last slide, that's fine. It's all written there, so you can just go back and watch it again later. Okay, let me show the results because it's interesting. We have a roughly equal split between true and false. So I guess I did go over this slide a bit too fast, maybe. It could also be that you're still not very familiar with these notations, so it was a bit confusing. The correct answer is yes, this is the same. And let me briefly go back and show why. if you have the set of strings here, the sigma star is the union of sigma to the n for all n greater equals 0. The sigma plus is the same union but starting at 1. And the only single string of length 0 that has no characters at all, that is the empty string. So really the only thing missing in this set compared to this set is that single string. So that's why we get this equation. Okay, fine. That's again, as I said, it's just a lot of information and notations thrown at you, but it's not really anything particularly deep. I do want to define the problem at least today that we will look at in detail next week, and that's the string matching problem. So suppose we're given a small pattern string, relatively small, it's not necessarily very small, and a fairly large text that we want to search. So we'll usually denote by T the text, T like text and P like pattern. I hope that is intuitive enough. People sometimes also call it finding a needle in a haystack, but I don't like that metaphor too much because that sounds like it's very hard to do. Whereas string matching is a problem that is very efficient to solve in practice. There's no problem really. So finding a needle in a haystack sounds really tough. And as I said, as a wake statement, usually we think of the text. The text has length n, the pattern has length m. We typically think of the text being much bigger than the pattern. Okay, well, I mean, the obvious application is you open a text file and it contains, I don't know, the text of Moby Dick, and you're trying to find all occurrences of whale in Moby Dick. Then the text is, well, I don't know how long that will be, a couple of million characters maybe. And the pattern is just, well, five characters, or maybe you want to find a little more specific whales, but it's fairly small in this example. What is the output? And this is, again, this is important to get the exact details of the pseudocode right at the end. I will always formulate the problems so that we find the first occurrence of the pattern in the text. So the smallest index at which we find the pattern in the text if we take the substring of length m of the text starting at that position. Okay? That's the formal definition of the problem. If there is no match, which could just as well happen, then we just return this dummy result, no match. I should say that there are variations of the problem, which could be find all occurrences, or some variations where you start at a certain position in the text. Starting at a certain position can formally be just treated as giving in a different text. Finding all occurrences is usually the same as this one. You could essentially just find the first match and then find the first match after this one. So you can iterate through all the occurrences. There's a slight catch to this that I will comment on at the appropriate time. But you will find in textbooks sometimes this variant is the one they study. I think this one is just as general, maybe even more general. So we'll always find the first occurrence. Okay, here's this variant, as I just mentioned. A small example, if you have this text and this pattern, then you actually find the first occurrence here. Maybe in red instead. And you don't find the pattern who. Of course, he occurs a second time at this end here, but we just return the first match. An algorithm for this problem is implemented in Java in the standard library in the method indexOf. And it's actually the brute force method, at least when I last checked. But we'll come to that.